Hey guys, welcome to the next video in the substitution elimination video set. This one we're going to be going over terp butoxide, or like those bulky bases, and we're going to go through a practice problem. All right, so let's just get started. So just in case you forgot maybe what terp butoxide looks like, it's going to look something like this. So an oxygen with a negative charge bound to a carbon with three methyls coming off of it. So we call this a bulky base. All right, so what exactly does this essentially, how does this change anything we've done that we've already seen? And also, just in case it comes up, there is one other bulky base you should be familiar with called LDA. This is just probably something you can put in your index card, not worry too much about. It's just a nitrogen that looks like this, bound to these substituents and a negative charge. All right. So yeah, just in case, maybe just put that in your index card. You may or may not see it, maybe with lithium plus on it, but again, it's the same thing. All right. So I'm just going to be focusing mainly on terp butoxide. This one, LDA, works the same exact way. So what do bulky bases do, right? So what I'm going to do is I'm going to draw the structure here. All right. And we're going to determine the product if I use OH minus. So if you want to pause the video here and figure it out for yourself, please feel free to do so. So we have a secondary good leaving group. Okay. So right now we could do SN1, SN2, E1, or E2. So we need to look at our nucleophile or base. We have OH minus, which is a small, strong base. All right. Because it is a strong base, right, we can eliminate SN1 and E1. And because it's a base on because it's a strong base on a secondary leaving group, we can eliminate SN2. So we're going to go through an E2 reaction. Now, we're going to grab the hydrogen right over there because that's going to form the more substituted double bond. Now, I have not drawn any stereochemistry here, and this specific example, we're going to not look at stereochemistry. So we're going to grab that H. That collapses, kicks out the bromine, and we're going to get this product. Okay? Now, what if I change the OH minus to terp butoxide? So let's just erase this. So here we're going to draw this. How does this change anything that we've done? All right, so terp butoxide is a bulky base. So the problem with a bulky base is this hydrogen over here, right? It's on a tertiary carbon. So it now has to navigate all the way through, make sure not to hit that methyl, and get around it. And so because it's so bulky, it's hard for it to do that. Similar to when we looked at SN2. SN2 is limited because the nucleophile has a hard time getting to our leaving group, right? So you can think of it in a very similar way for the E2. For the bulky base E2, all right? And so because this is a hindered or bulky base, to get to that one hydrogen is a little bit difficult. So what instead it's going to do is it's going to go for one of the hydrogens right over here. Because you see there's two of them, it's easier, it's not as hard for it to bypass a bunch of other things on here, the secondary carbon. So it's going to go for that one of those blue hydrogens. So it's going to grab this hydrogen. That bond collapses down and kicks the bromine out, giving us something that looks like this. The less substituted alkene, if you remember, what we got before was this. So you can see the difference. We formed the least substituted double bond with terp butoxide, whereas with a small bases, we form the more substituted double bond. Okay? Now, one thing to keep in mind is that even though we're forming the least substituted double bond, this does not change the fact that in an E2, you must use you must take a hydrogen of opposite stereochemistry. Okay, that has not changed. So now we're going to do this with stereochemistry. So I'm going to make my Br wedged. I'm going to make the methyl here wedged. This hydrogen is going to be dashed. And then we have, remember, two hydrogens on that carbon, one wedged, one dashed. So in this case, remember, terp butoxide still is going to take the hydrogen of opposite stereochemistry. So it's going to grab that hydrogen, and we get this. So we're going to now have this product. All right, same thing. Now, what if I decided to change the stereochemistry a little bit? Okay, so what I'm going to now do is, hold on a second. So I'm going to change the BR dashed. Okay, let's just do this. Okay, so we have this example. All right, so now we're going to try to figure out how this is going to work. So we have a terpetoxide. Again, we have a surrounded by with the secondary leaving group. The two carbons next to it are equally substituted, right? One has a wedged methyl with a dashed hydrogen, and the other one is a dashed methyl with a wedged hydrogen. Let's just draw that hydrogen there. Okay. So which hydrogen are we going to take in this case? Well, again, remember, we take the hydrogen always of opposite stereochemistry, and we try to form the least substituted double bond. Okay. Now, in this case, there is no way to form the least substituted double bond, only because whichever double bond you form, left or right, it's going to form an equally substituted double bond. But again, we can only grab the hydrogen that's opposite stereochemistry. So in this case, since the Br is wedged, we're going to grab this dashed hydrogen, giving us something that looks like this. All right, giving us that product. All right, now, like I said before, E2, the rule that we grab the hydrogen that's opposite stereochemistry cannot be broken. So if they give you a situation where the hydrogen that you have to take, where they reacted with terpetoxide, and the hydrogen that you have to take to form the least substituted double bond is the same stereochemistry as the bromine, we cannot take it. Even if that means that the only hydrogen we can take will form the more substituted double bond. As long as it's anti, it's okay. But under no circumstances can we break the rule that the hydrogen must that the hydrogen has to be opposite the stereochemistry of the leaving group. That can never be broken. All right. So what we're going to do is try a practice problem. Right here, this is my review problem set. So it's asking us to draw the major product of the following reaction, showing wedges and dashes where appropriate. Okay. So first thing we need to do is figure out what our reaction is. So we have a tertiary leaving group. So right off the bat, we can eliminate SN2. We cannot eliminate SN1 and E1 based solely on primary, secondary, tertiary, because tertiary carbocations are stable. So what we now need to do is look at what we're reacting with. We're reacting with terpetoxide, which is a strong, bulky base. The fact that we have a strong base means we can eliminate E1 and SN1. So we're going to go E2. Now remember, because terpetoxide is bulky, we're going to want to form the least substituted double bond. So let's look at the two carbons to the left and right of our carbon with the leaving group. The carbon on the left has a wedged hydrogen. The carbon on the right has a dashed hydrogen and a wedged hydrogen. Okay? So we always have to take the hydrogen that's opposite stereochemistry, and our bromine, our leaving group, has a dash bond. So that means the hydrogen we take must be wedged. So that means we can take the red hydrogen, because they're opposite, and the wedged blue hydrogen on the right. So what I'm going to do is I'm going to draw both products. Okay? So the mechanism of terpetoxide grabbing the red hydrogen would look something like this. Grab that hydrogen. This bond collapses, kicks the bromine out, giving us something that looks like this. Remember, any substituent off of a carbon with a double bond must be planar, okay? Always. If we drew one of those like this, right, that's going to get you points off the test. It must be planar. So we leave it like this. So that's if we grab the red hydrogen. Now let's try grabbing the blue hydrogen. So this is going to come down, grab the H. This bond gets collapsed downward, kicks the bromine out. So now what we're going to have is that methyl that was wedged is going to be over here. We're going to have a double bond there. And the methyl, the dashed methyl on the left is going to stay dashed because we didn't touch it. So let's look at these two products. The double bond is more substituted on the left versus the right. All right, and so because we know terpetoxide would rather grab the least substituted hydrogen, we're probably thinking that the one on the right is going to be the answer to this question. But there's one thing we did not look at, right? What about the hydrogens on the methyl that's wedged? All right, so I'm going to redraw this, the original reactant. Okay, so what about the hydrogens on that methyl? They're still perfectly, they're still the correct distance away for an E2 reaction, right? So what if I grabbed one of them? Well, I'm going to put my terpetoxide. Let's move this stuff away and bring this a little bit closer. So now I'm going to put my terpetoxide. Let's draw it in green. Grabbing one of those hydrogens and see what we get. This is going to come downward, kicking the bromine out. So what we're going to get is still the dashed methyl over there. Our leaving group is gone, but now we get that double bond. So we have three possible products that we can pick from, right? These three over here. Which one is it going to be? Is it going to be number 1, 2, 3? Well, we know that number 1 is the more substituted one, so if we could, we'd avoid that one. So we can eliminate number 1. Number 2 is less substituted than 1, but when we compare it to number 3, 3 is even less substituted because we only have hydrogens coming off here, right? Because this double bond on number 2 is connected to 1, 2, 3 carbons, whereas number 3 is connected to 1, 2. So 3 is the less substituted product. So we would actually answer this question as going with number 3. All right, so you can see that that's not a very obvious answer. Most people would have gone with number 2, right? Which is going to be the more obvious and looks like it'll be, yeah, just because it's the more obvious one. But remember, we would try to form the least substituted double bond. So don't be afraid to take it off of a methyl, okay? That does happen, and that is a way that they could disguise what looks like a very obvious and easy question with a little bit of a trick to it, okay? So the answer to this question would have been 3. Okay, so in the next video, we're going to be covering how we deal with alcohol leaving groups. Up until now, the only things you guys have seen in these videos are halide leaving groups, right, or halogen leaving groups. Now we're going to deal with alcohols, okay, because that's like a whole nother class of leaving groups and how we deal with them versus the halogens. It's not the same. All right, so I hope this video helped you guys. If you're confused about anything, please feel free to go to the CLC, talk to the TAs. You can email me, or if you're watching this on YouTube, leave a comment with your question, and I'd be happy to answer it. And I will see you guys in the next video.